Who has more pens? Soumya. But how can we get the answer? Simple. Compare the number that they had imagined. What will happen if there is no number? Simple questions would be practically unanswerable. Number is of huge importance in our daily life. Real numbers include rational and irrational number. Let us first look at rational number. For example, 1 by 2, 5 by 2, 3 by 7, 5 by 3, 2 by 1 or 2. These are all rational numbers. That is, the number is of the form p by q, where p is equal to 0 and q is equal to 1 are integers, and q is not equal to 0, is called a rational number. Now we take two rational numbers, 1 by 2 and 3 by 2. How many rational numbers are between these two? Think about it. You will find out infinite rational numbers between any two rational numbers. Let's check it. Example. Is 7 minus 2 root 5 plus 2 root 5 a rational number? Solution. We have 7 minus 2 root 5 plus 2 root 5 is equal to 7 minus 2 root 5 plus 2 root 5 is equal to 7. We can write it as 7 by 1. Thus the number 7 minus 2 root 5 plus 2 root 5 is a rational number. Similarly, square root of 49 by 81 is equal to 7 by 9 is of the form p by q, where p is equal to 7 and q is equal to 9 are integers, and q is not equal to 0. Hence, square root of 49 by 81 is a rational number. Example. Find 5 rational numbers between 2 and 3. Solution. To find a rational number between r and s, you can add r and s and divide the sum by 2. That is, r plus s divided by 2. So here r is equal to 2 and s is equal to 3. Therefore, 2 plus 3 by 2 is equal to 5 by 2. 5 by 2 is a number between 2 and 3. Similarly, we can find other rational numbers between 2 and 3. Hence, 4 more rational numbers between 2 and 3 are 9 by 4, 11 by 4, 23 by 8 and 21 by 8. In general, there are infinitely many rational numbers between any two given rational numbers. Now look at the irrational number. For example, root 2, pi, root 7 or root 15. They are irrational numbers. That means the number which cannot be written as the form of p by q, where p is equal to 0 and q is equal to 1 are integers, and q is not equal to 0, is called irrational number. Look at the example. Pi or 3.02145789321 and so on is irrational number, and root 4 is equal to 2 or minus 2. So it is rational number, or root 4 is not irrational number. All perfect roots are rational numbers. Pi is irrational number, but if we write pi is equal to 22 by 7 approximately, it is rational number. But actually pi is an irrational number. Now 0.121, 221, 222, 12 and so on is irrational number, as we see that the number of 2's between the 1's keeps on increasing by 1. The irrational numbers are the part of a set which has decimal numbers that neither terminate nor repeat themselves. Look at the given examples of irrational number. These numbers are not perfect square, so it cannot be written as P by Q. Let us consider an example. The decimal expansion of this number is non-terminating and repetitive. Repetition of 896. Hence this is a rational number. It looks like a non-terminating and repeative decimal number. However, it is a non-terminating and non-repeating decimal number, as the first 6 digits after the decimal are 193193, repetition of 193. But the next digits are 1934. Hence altogether no number is repeating itself. Hence it is an irrational number. Representing irrational number on number line. Let us represent root 10 on the number line. Now one way of doing it would be that we construct consecutive irrational number, that is root 2, root 3, root 4 and so on them. We get root 10, but these could be rather time consuming. So we can do this. First take OA on the number line between 0 to 3, that is 3 unit. Now construct a perpendicular so that AB is 1 unit. Now join OB. Take compass and draw an arc from the point O with length OB. The arc intersects on the number line at D and it gives the length of OD, that is root 10. This method is much easier. Do you agree? Yes. Let us apply Pythagoras theorem in triangle OAB. OA equals to 3 unit and AB equals to 1 unit. So the square of hypotenuse OB is equal to OA square plus AB square. That is 3 square plus 1 square equals to 10. OB equals to root 10 unit and also OD is root 10 units. This method is faster and easier to construct irrational number on the number line. Here we are going to represent root 5.6 on the number line. How do you do that? First draw a line and mark P and Q such that PQ is equal to 5.6 units. Now mark another point S such that QS is 1 unit. Now mark another point O, that is midpoint of PS, so that OP is equal to OS. Place compass at the point O and take radius OP and draw a semicircle as given here. Draw a perpendicular line on Q and meet it at point R. Take Q as center and draw an arc with length of QR as shown here. This arc intersects at point T and length QT is root 5.6 units. Let us justify this construction. PS is equal to PQ plus QS is equal to 5.6 plus 1 is equal to 6.6. PO is equal to half of PQ, that is 6.6 by 2 is equal to 3.3 unit. We know that PO is equal to OR because it is the radius of the semicircle. Thus OR is equal to 3.3 units. What about the OQ is equal to OS minus QS is equal to 3.3 minus 1 is equal to 2.3 unit. Using the Pythagoras theorem in triangle OQR, QR square is equal to OR square minus OQ square is equal to 3.3 square minus 2.3 square. Finally, reducing this, we get the square root of 5.6, that is QR. You remember that constructing the arc QR is equal to QT. Thus we justify the construction. Real numbers and their decimal expansions. Let us start with a few examples of rational numbers. Find the decimal expansions of 5 by 8, 4 by 3 and 2 by 7 rational numbers. We use the long division method here, as we can see that in one case the remainder is 0 and in the other two cases it is not. Therefore, we can now have two separate cases. Case 1, when the remainder is 0. In this case, the remainder is 0 and the decimal expansion terminates after a finite number of digits after the decimal point. In the decimal expansion of 5 by 8, we can see that the remainder becomes 0 and the decimal number obtained is 0.625. Case 2, when remainder never becomes 0. In this case, the remainder never becomes 0 and the corresponding decimal expansion is non-terminating. And in the decimal expansion of 4 by 3 and 2 by 7, we can see that the remainder never becomes 0. Thus their corresponding decimal expansions are non-terminating. The decimal expansion of rational numbers is either terminating or non-terminating and repetitive. Whenever we divide 2 by 7, we get 0.285714285714 and so on is equal to 0.285714 bar. Here 0.285714 bar means that the group of digits 285714 is repeating. Similarly, we can write 17.450236236236 and so on as 17.450236 bar, because only the group 236 out of the group 450236236236 is repeating. Hence we put the bar symbol as shown only on 236 and not on the whole group, that is 450236236236. Now consider the irrational number pi. The approximate value of pi is 22 by 7. The decimal expansion of pi is 3.14159265358 and so on, which is non-terminating and non-repetitive. In the same way, the decimal expansion of the square root of 2 is equal to 1.414213562373 and so on is non-terminating and non-repetitive. For irrational numbers, the decimal expansion is non-terminating and non-repetitive. Example: write the decimal expansion of 3 by 7 and find whether the number is rational or irrational. Solution: the decimal expansion of 3 by 7 using the long division method as shown is 0.428571, 428571 and so on is equal to 0.428571 bar. Hence the decimal expansion of 3 by 7 is non-terminating and repetitive. Thus the number 3 by 7 is rational. Conversion of decimals to fractions. We know how to convert decimals into fractions. Let us consider some fractions and convert them in their decimal forms. First, look at the steps to convert a decimal into a fraction. As first, we count the number of digits after the decimal. Let it be p and write the fraction as given number without decimal point divided by 10 raised to the power p and then reduce the fraction into simplest form. Let us look at some example. What is the fraction form of 6.5? As in 6.5, there is only one digit, that is 5, after the decimal. So the value of p is equal to 1. Hence we can write 6.5 as 65 by 10 raised to the power p or 65 by 10 raised to the power 1. That is 65 by 10, which is equal to 13 by 2. Now what is the fraction form of 0.54? As in 0.54, there are two digits that are 5 and 4 after the decimal. So the value of p is equal to 2. Hence we can write 0.54 as 54 by 10 raised to the power p, or 54 by 10 raised to the power 2, that is 54 by 100, which is equal to 27 by 50. Similarly, we can write 0.9 as 9 by 10, 0.593 is equal to 593 by 1000, and 0.00243 is equal to 243 by 100,000. Now let us solve the given example. Show that 1.272727 and so on is equal to 1.27 bar can be expressed in the form of p by q, where p and q are integers and q is not equal to 0. Solution. Consider 1.272727 and so on equals to x. Since two digits are repeating, we multiply x by 100. We get 100x is equal to 127.2727 and so on. 100x is equal to 126 plus 1.272727 as 1.272727 and so on is equal to x. So 100x is equal to 126 plus x. Therefore 100x minus x is equal to 126. So x is equal to 126 by 99 is equal to 14 by 11. We can check the reverse of it, that is 14 by 11 is equal to 1.27 bar. Representing real numbers on the number line. Look at this number 5.8346. How can we represent it on the number line? Let's see. 5.8346 lies between 5 and 6. If we want accurate visualization, we need to divide it into 10 equal parts between 5 and 6. And let us magnify there. 5.8346 lies between 5.8 and 5.9. Now further divide 10 equal parts between 5.8 and 5.9 and then magnify them. Now look at this number line. Go back to 5.8346. It lies between 5.83 to 5.84. Repeat this process. Magnify and divide into 10 equal parts. Go back to 5.8346. We put the three decimal numbers on the number line. 5.834 lie between the 5.835. So divide this number into 10 equal parts and magnify them. Now we can see 5.8346 at this number line. Thus we get the 5.8346 on the number line. Operations on real number. Let us consider some examples and solve them. Example. Add 2 root 2 plus 5 root 3 and root 2 minus 3 root 3. Solution. 2 root 2 plus 5 root 3 plus root 2 minus 3 root 3 is equal to 2 root 2 plus root 2 plus 5 root 3 minus 3 root 3 is equal to 2 plus 1 into root 2 plus 5 minus 3 into root 3 is equal to 3 root 2 plus 2 root 3. Similarly, by solving 6 root 5 by 2 root 5, we get 60. And again by solving 8 root 15 divided by 2 root 3, we get 4 root 5. Now these examples may lead you to expect the following facts which are true. The sum or difference of a rational number and an irrational number is irrational. The product or quotient of a non-zero rational number with an irrational number is irrational. If we add, subtract, multiply or divide two irrationals, the result may be rational or irrational. Laws of components of real numbers. Some important laws of components are given here. The first law says that x raised to the power m into x raised to the power n is equal to x raised to the power m plus n, which means if two or more numbers with same base are multiplied, then answer is base power raised to the sum of powers, where m and n are integers and x is any non-zero integer. Let us do some questions for better understanding of the formula. Example: simplify and write 18 raised to the power 5 into 18 raised to the power minus 7 in exponent form. Solution: the bases are same, so by using the formula x raised to the power m into x raised to the power n is equal to x raised to the power m plus n, we get 18 raised to the power 5 into 18 raised to the power minus 7 is equal to 18 raised to the power 5 minus 7, or 18 raised to the power minus 2. Similarly, simplify and write 2 raised to power 2 by 3 into 2 raised to the power 1 by 3 in exponent form. Solution: bases are same, so by using the formula x raised to the power m into x raised to the power n is equal to x raised to the power m plus n, we get 2 raised to the power 2 by 3 into 2 raised to the power 1 by 3 is equal to 2 raised to the power 2 by 3 plus 1 by 3, or 2 raised to the power 3 by 3, or simply 2 raised to the power 1. Now the second law that we are going to study is x raised to the power m by x raised to the power n is equal to x raised to the power m minus n. This means if two or more numbers with same base are divided, then the answer is base power exponent power minus lower exponent. Let us understand with the help of an example. Simplify 7 raised to the power 1 by 5 divided by 7 raised to the power 1 by 3. Solution: we have 7 raised to the power 1 by 5 divided by 7 raised to the power 1 by 3 is equal to 7 raised to the power 1 by 5 minus 1 by 3 is equal to 7 raised to the power minus 2 by 15. Now the third law is x raised to the power n raised to the power m is equal to x raised to the power m into n, or x raised to the power mn. Let us see some examples. 3 raised to the power 1 by 5 raised to the power 4 is equal to 3 raised to the power 1 by 5 into 4, or 3 raised to the power 4 by 5. And the last law is x into y raised to the power n is equal to x raised to the power n into y raised to the power n. For example, 13 raised to the power 1 by 3 into 17 raised to the power 1 by 3 is equal to 13 into 17 raised to the power 1 by 3, or 221 raised to the power 1 by 3.